is from FISH Technology, and she's going to tell us about in situ hybridization diagnostics, looking at falciparum. Dr. Shah is Vice President and Laboratory Director at IGeneX Laboratory, and also Founder and Vice President of Research at FISH. She did her Ph.D. in immunology at Nairobi University, has worked in the biotech field for quite a while, and I believe 16 years at IGeneX. So thanks very much, and without further ado.
Thank you for allowing me to speak here today on fluorescence in situ hybridization. It's something that I've worked for years. It started out as a research tool when you couldn't culture, for things you couldn't culture. It started with pneumocystis carinii. I'm going to give you a little background and then jump into malaria fish assays. Introduction, current status, future. So what's our mission? What we wanted to do at FISH Technology, FISH meaning infectious disease fluorescence in situ hybridization, so we just call it FISH Technology, was to develop inexpensive, easy to perform tests that could be useful in underdeveloped countries where the disease is a big problem. Infectious disease like malaria and TB are big burden. That is the goal of FISH, develop simple, inexpensive tests. And we feel that fish may be the right way to do it. I'm not going to go into all that because this is a group who knows malaria, so let's just skip all of that. So the current test that is GIMSA, RDT, PCR, and QBC. These are the current tests that are used for diagnosis of malaria. The most common being GIMSA and RDTs. But they have their problems. So history about fluorescence in situ hybridization. Initially described in 1969 for clinical use. 1989, when fluorescence in situ hybridization was introduced for environmental bacteria and fungi. And in 1991, we demonstrated the use of fish assays in clinical samples. So the work was done in, the first paper that was published was from Dr. Norman Base's lab, and Edward DeLong was the one. This group used to look at bacteria in Yellowstone National Park, really deep down hot springs, basically, is where they were looking for bacteria and fungi. They didn't know what they were finding. And in order to identify whether they were bacteria, fungi, parasites, what, they designed some probes, bacterial probes, fungal probes, and then they looked at what they were bringing from there, deep down, and looked at that. And this is where fish was first used to show that you can detect bacteria and parasites using fluorescence in situ hybridization with short oligos. And then we were working on a project on developing probes for pneumocystis carinii. This is in the early 1990s, where with the coming of the AIDS, pneumocystis had become a big problem. Before, pneumocystis doesn't really cause disease in normal patients, but if you're immunocompromised, it's an opportunistic infection and you get it. But the biggest problem with pneumocystis was that you cannot culture it. So if you are trying to develop something for pneumocystis carinii, how are you going to validate your system? What is required? So this is where we say maybe we can develop a test that we can use using what Dr. Base's lab had shown that they had been able to look at bacteria and fungi using fish technology. So this is where we decided to investigate fish for pneumocystis. So what is fish? Basically, we are targeting the ribosomal RNA of the organism. And what we do is we design probes that will target specifically the ribosomal RNA of interest. You hybridize to the whole cell, fixed cell, then you wash off the excess probe and you look under the microscope. The advantage is because ribosomal RNA is present in the cytoplasm, you can see it. The copy number is very large, you don't need amplification, and you can see. So you have the specificity of the probe plus the morphology of the organism. And that is why we felt that this was a good technique to look at biopsy samples when we were doing pneumocystis or sputum samples. The main reason why we chose fish as a method. This is an example of a sample that was done at Brigham and Women's Hospital by the scientists there. Once our probes were designed and we were working with them, they provided us with the real patient sample to develop probes for Pneumocystis carini. And what we did was, once we had designed the probes, we gave the probes to them to look at with the FISH technology. And here what they did was, this was a sputum sample, induced sputum sample. This is stained with the monoclonal for Pneumocystis carini. And on this side, the same sample was stained with the probe. So it's a dual system where you stain it with the monoclonal and the probe to demonstrate that what we were picking up with our probes was really specific for Pneumocystis carini. This is another example. What happened was we were given infected ferret tissues. And at the time we were doing this study, we didn't even know whether there was just one species of Pneumocystis carini or there were different strain species. We had no idea. Nobody really had an idea. When we got this sample, ferret tissue, which was our model system to develop the whole genes and design probes, we found that when we did the cloning, about 9 out of 10 clones had one sequence and then the other one had a different sequence. The question was, were there two different species or strains in the ferret, or was it two different stages of the parasite? We didn't know what it was, because at that time, one of the thoughts was in parasites, that there were two different stages of ribosomal genes that were expressed, one in the asexual form and one in the sexual form. So we wanted to see what happens with this technique. And what we found really here was that there were two different species of the parasite. If it was that all of them had both genes present, we should see a mixed signal. We didn't see a mixed signal. We saw clear red and green signal here. So that told us that this technique was pretty powerful. As you can see, this is one species and then we had two color probes. One was red, one was green, and most of them were red, few of them were green. So that clearly showed us the power of this technique. Another example, this is Babesia duncani. Babesia is an upcoming disease here in the States. This is transmitted by ticks. It's very similar to Plasmodium falciparum. And what you're seeing here are the rings. This is a hamster tissue which we have here. Sorry, not tissue, blood sample from a hamster infected with Babesia duncani. And the probe we used was a Babesia specific probe. And you can see beautifully how it stains the parasites. So basically, this technique is very simple. It's very rapid because all you're doing is hybridization. There is no sample prep, no amplification, just hybridize, wash and look under a microscope. It's almost like staining, but with a very, very specific probe. So the staining is very specific. And the reason we get a high sensitivity is because ribosomal genes, the copy number is very large. Anywhere from bacteria can be minimum of 1,000, going all the way up to 10 to the 5. So the only requirement here is a microscope. And what we have been able to show, the specificity is equivalent to amplified assays, because what defines your specificity is the probes, or the sequence you choose is going to define your specificity. So when we compare GIMSA, PCR, FISH, and RDT, what you see is GIMSA detects whole parasites, provides you with the morphology. PCR doesn't give you that, but it's very specific because you're targeting DNA. FISH, the advantage is you can target RNA or DNA using fluorescence in situ hybridization. RDT is very simple. It looks for the antigen or antibody on a strip. Very easy, doesn't require any other equipment to do it. Extraction, GIMSA doesn't require any. PCR, as you know, will require some extraction procedures. FISH doesn't and RDT doesn't. So if we really go down, the difference between GIMSA, so I have made a mistake. It detects dead and live organisms, and it provides you with morphology. It's the PCR that doesn't provide you with morphology. I made a mistake here. And it only detects DNA, so you cannot differentiate between dead and live organisms, nor do you get morphology when you use PCR. With the FISH, you only detect live organisms because we are targeting ribosomal RNA. We're looking at RNA, not DNA. In terms of RDT, it detects live and dead organisms. So that's the big difference with FISH technology. You look at live parasites. With all the other ones, you cannot differentiate between live and dead parasites. Provides you with morphological information. Ribosomal genes are very unique. You can design genus level probes, species level probes, and strain level probes. And the molecule is so diverse, and that is what we have taken advantage of to develop FISH assays. Malaria FISH assay. So we talked about it. It's highly abundant. Therefore, it's possible to design all the different types of probes, and it targets the cytoplasm, so you get the morphological information. So this is our kit, and what we have done in terms of the microscope is we just use a regular microscope with an LED unit. And that was one of the biggest questions. If we are going to develop a test for malaria, which is endemic in countries where fluorescent microscope can be a big issue because of maintenance, and also it's expensive. So we have developed a unit which can be attached to a regular microscope, LED unit, which has two filters in it. A red filter, or orange filter, and a green filter in there. And this unit can operate on a battery. We can mix, the way we design this probe, we can mix and match. We can design genus or PF and PV, and currently we have also developed a PV-PF combo assay so that you can differentiate PF and PV on a single smear. And this is being evaluated currently. So I just want to point out the way the genus kit uses a green probe. So if you are hybridizing with a genus probe, you will see a green signal. With the PF kit, we have a genus which is red and a PF which is green. So we are using double probes. With the PV also kit, we have a genus which is labeled with the red color, and the PV specific is labeled with the green color. And the reason we did that was to increase the specificity. Really, you're using two probes. The chance of to give you a signal with two probes, a positive is going to be very low for a false positive. This is to show you that the assay is semi-quantitative. What we did was for limit of detection, we took vivax or falciparum parasites, diluted them in blood, and counted them to see what we were detecting. Was this assay can this be used for semi-quantitation or not? Or was the answer going to be yes or no? And we were quite surprised because once we looked at it, it turned out to be a pretty straight line graph. If you look at the R-square value is very, very high. So the assay was very linear, so we believe that the fish, because we are able to count the parasites, just like Giemsa, can be used to quantitate the parasites. So that was an added advantage that we found out from our studies. And the limit of detection was around 60. In this study we found for the fish was around 60 parasites. So that's where we are with the limit detection. And then looked promising, so we did a clinical study. And this study has been done on 535 patients from the endemic region. We got 302 samples from Kenya, from India we got 302 samples, Kenya 205 samples, and Peru 28 samples. And we took 150 patient samples from the United States as our negative control. So follow the protocol. We ran the genus test, PF and PV test on them. And we also did PCR on a subset of samples for discrepant analysis. And also ran some RDTs on them. And if the fish sample was either positive by RDT, ICMA or PCR, it was considered a true positive for discrepant analysis. Just to show some pictures, this is P. falciparum positive sample. Red is the genus from here. P. falciparum, red genus, and green specific probe, same sample. Look at the data now. Very simple. The sensitivity without discrepant analysis, before discrepant analysis, compared to Giemsa, fish was 96.9%, specificity was 80%. It's really bad here. Falciparum, 100%, 94, 191%. Specificity, vivax, 97.6, 91.6. After discrepant analysis, what we found was the sensitivity of Giemsa was 81%, fish was 97%, specificity of Giemsa was 100%, with fish we got 94%. Falciparum, sensitivity was 83%, 95% with fish, specificity was 100%, and for fish it was 98%. With the vivax, sensitivity was 75% with Giemsa, fish was 98%, specificity of Giemsa was 100, and fish was 96. So clearly, fish is a technique that can be used clinically based on this data. It has very high specificity. What we find is that probably, compared to PCR, fish is very easy to do. You don't need special rooms. You don't need to extract DNA. You just do it on the sample. And the data clearly shows that fish has value for diagnosis of malaria. It's very simple because with the LED microscope, you can do this anywhere. Don't need a fancy lab to run fishes. This is just to show you in terms of parasites, there are no, we were able to detect up to 200 parasites, 100% of the samples, around 100 parasites. It was 88% sensitivity, under 100 was 86. So even at the low end, the sensitivity is not that bad. In the venous blood, 100%, around 100 it was 94.2%, under 100 it's about 81%. So overall, we were able to detect 95% of the venous blood. Now, one of the reasons why the numbers might be a little lower than Giemsa, as I mentioned, Giemsa detects live and dead parasites, whereas with the fish we're detecting live parasites. And we have done studies, which I'm not going to show you here today, but what we did was we worked with Walter Reed in Nairobi, in Kisumu, and they were doing a drug study on children. and they were collecting samples every 8 hours up to 72 hours. We looked at 8 patients with them. They ran Gimza on those samples. With the leftover samples, they made smears for fish and sent it to us. So we got all these smears. We ran fish on them. It was very, just to give one of the pair, the fish always was earlier in terms of where it became negative, which is not surprising. And then Gimza became negative following that. So fish was giving answers earlier because we're looking at ribosomal RNA when it's still there. And if you look at the signal on at point 0, if the drug is working, the signal is very bright. As time goes on, the signal fades. When you can see that, and then it's dead. So I think this could be this may explain why the sensitivity appears to be lower, because in this study, we did not choose just new patients. This was a study with any sample that came in for any patient came for with malaria-like symptoms were tested. Just to give you, this is our combo kit, PFPV kit. On this side, I have a sample that was P. falciparum positive, as you can, and the P. falciparum probe is labeled green, and the P. vivax probe is labeled orange. And you can see it's pretty clean. On this side, you see the PV and PF probe is, the green probe is, there's no signal on that, but on the PV side, you see the bright orange signal. And this kit is currently being evaluated. So in conclusion, what I have is it's a rapid test, about an hour. It can be performed directly on blood smears. It is semi-quantitative, sensitive and specific. In addition, provides parasite morphological information, and we believe that it's technically feasible in the developing world by using battery-operated LED microscope. You will not require highly trained microscopist because you're looking at a bright signal. It's not, you're not trying to look at just the morphology, where sometimes if staging is not good, you may say, yes, it could be a platelet, it could be a parasite. The results that we had here for Gimza were done by experts. It wasn't like just any lab that had looked at the Gimza results. So clearly, and we have, in fact, our experience now is that we have trained people in different parts, and they pick it up fairly easily if they have some background knowledge about microscopy. They find it very easy to read the slides. So a study like this is not possible without the help of collaborators. First of all, at FISH team, and I would like to thank Olivia, who has done most of the work here. She is the scientist who has been behind a lot of the study designs and has really put in several years of work on it. Nicholas was with us for 2 years. These are the key people who helped us get through the project. Our collaborators have been Cambridge, Kenya, Dr. Sabha Amar, Dr. Srinivas, Dr. Rao, Shaila Bhatt, Dr. Gilman, for Peter Obeir, Ruchi Sinha, and many more. And this work was supported by NIH SBI grants, phase 1 and 2.
Questions for Dr. Shah?
I suppose it's most useful for you if we ask you hard questions, right?
Yes.
So what do you intend this? Well, first of all, is the kit available? Is it actually commercial yet?
No, it isn't, because in US, you have to get an FDA approval.
So that's your plan, is to go?
That is our plan. In fact, what had happened was we had talked to FDA quite a while ago. And when we first talked to them, they told us we could not use PCR for descriptive analysis. We had to use FDA cleared test, and that was RDT. Clearly, the drug was not true. So we went by their rules and said, okay, if they want us to do RDT, we'll do RDT. And we presented the data to them. Then they came back and said, oh, your test is more sensitive. They could see that. And they said, that's all false positive. You can't put it that way. So So I said, you told us not to do PCR. We refused, I mean, that wasn't an accepted method at the time. So you have to, and they set guidelines like you had to have your confidence intervals between 90%, 90 and 100%. With the data we had, we could not put it in that format because we were more sensitive than GINSA. They wouldn't let us use, RDT was out, PCR could not, we could put it as a footnote, but could not do analysis with that. So they said, well, we've changed the rules now, we know better. RDT is not good, they're not going to allow you to do that. Your only choice is to go back and do PCR all the samples. Not only that, you have to sequence. Okay, this is what happened after we had consulted them before we even started. When we presented the data, that is what they told us last year, exactly a year ago. So, by that time, we did not have enough samples to go and sequence every sample. We had to start all over again. And we have started that process. Our collaborators were wonderful. They've been giving us the samples, they're working with us. And we are hoping that we will get some funding from NIH to finish this study. They've been very helpful, but that meant a lot of extra work we ended up doing.
So my question is, you intend this to be a routine test in rural clinics in Africa and India?
I think it's going to be more of a central lab because I feel that the rural places may not want to do something like it. They might, it would be great if they do accept it, because once they have the platform for these, other diseases can be headed off.
Yeah, well, speaking for Africa, I mean, the challenges are great. And rural labs don't make decisions. They do what the government tells them to do, the Ministry of Health. They have very little resources. They really diagnose almost nothing other than malaria. They don't really have other tests available.
Right.
So they're doing very little, and they've been using GINSA for many decades. They like it. Now RDTs have come in, and they're becoming popular also. They are also easy. And so I think you have a real challenge to convince really governments or the WHO to replace very standard tests. You have some good arguments for why it may make sense to do that, but I can see it very challenging. While on the other hand, as a tool for researchers, it's much lower bar, and there are certainly situations where a highly sensitive test gives somewhat different information than PCR can be used.
So how much does the LED attachment cost?
It's actually available for research use. The kits are available.
Okay.
LED 3,000?
The LED unit with the filters and all is about $3,500.
So because your signal is pretty bright on the background, would you say that a microscope isn't really necessary even for this? So you could imagine a handheld device where you basically just read out fluorescence reading in the blood sample, and if it's above a certain threshold, then that should indicate that there are parasites, right? Because you're washing out the excess probe. So since this fluorescence unit is $3,500, you could have, I mean, it seems like you guys built or collaborated with someone to build this device. Could you imagine building a simpler device where you basically just, plug a vial of blood in or a slide, and then it reads out a number that basically says yes or no?
There are groups who are working on it. So, and, right now there is it's early stages, I'm saying.
It's not as simple as, to miniaturize it and say maybe read it on a cell phone or something. We haven't come across anybody that we could do that kind of work with.
So what is the cost of an individual assay? You already own the microscope. With the kit, purchasing the kit, what's the cost per assay?
Our target price is under $2 for the lab.
Yeah, there's still, again, to be honest, we're used to a world where treatment for malaria is a few pennies. It's a little bit more now with the new ACTs, but they're generally provided anyway by international funding. And it's a lot. That's still a lot of money. It's incredibly cheap, but it's the RDTs I think are in the order of $50 now. something like that.
Yeah, about 70%.
And my biggest worry about RDTs is that there's so much variability from
Yes.
manufacturer, it's a very poorly controlled environment, a lot of different companies making.
So I'm curious, just listening to the discussion, is there a target market or application that you think that this technology would fill that niche?
We believe that in central labs, this would make a lot of sense, where the samples may come from the smaller clinics, difficult cases, but also for QC research and epidemiological purposes, this would make a lot of sense.
Not only that, when we are in Africa, in Kenya, we look at the way the hospitals and local clinics deal with it, is that in the hospital settings, they don't want to use RDTs. They are either using PCR if they're a higher grade hospital, or they are still using gibbs staining. The RDTs are mostly done at the community level, where the RDTs are missing a lot of the low level infections.
Or very high levels as well.
Or very high level. But what we feel the niche would be is that at the community level, you would do the RDT, but at the district hospital level, for patients, they would use our technology, which is more sensitive and for specificity.
Other questions? Okay, thanks very much.